Hi, so this is lecture number 21 in ME303 heat transfer. We'll continue our discussion on convection today. We've been talking about the derivation of the convection equations, which ultimately will give us the equation for the temperature as a function of y, which can then be used to calculate the heat transfer coefficient h using del T by del y at y equal to 0 for different x values in the flat plate. Okay, we've been talking about flat plate, but that does not mean that these equations are only valid for flat plates. You may have curved geometries, such as let's say an aerofoil. So even in the curved geometry, if the flow is happening in this direction, then you may define an x coordinate which is along the curvature of the geometry. So in this case, your boundary layer may develop something like this. Let me only show you a two-dimensional picture here. Okay, so the boundary layer may develop like this. So the ideas may still be similar, and the equations that we're deriving will still work for curved geometries as well. Okay, so let us continue with our discussion. We were deriving the equation for convection in the previous lecture. So let's quickly draw the figure. So we had taken a control volume. So we had taken a boundary layer, then we took a small control volume inside the boundary layer, and then we zoomed into it, and we were doing an energy balance on this control volume. So we had term number 1, which was enthalpy, x flow enthalpy and kinetic energy. Then we had term number 2, which was x flow enthalpy and kinetic energy out. Then we had term number 3, term number 4, which were all enthalpies in and out. And then we had derived the expression till term number 4. And then next we have the term number 5, which is heat conduction in. And we had heat conduction out, which was term number 6. Okay, so let us write the expression for these terms. So for term number 5, that is the heat conduction in. We know that the watts or the Q is given as Q double prime, which is a vector dot the so this is how we typically define the watts because of conduction into the from the bottom surface. So here the Q double prime in the y direction, because we're talking about this y direction here. Remember, we said that the conduction in the x direction is neglected because the temperature gradients in the y direction are much higher than the x direction. So Q double prime, the vector is primarily in the y direction only. So we'll just write that as Q double prime for simplicity. And then the area is, well, the control volume size was delta x times the unit direction in the depth. So we have Q double prime times x. And this Q double prime from the Fourier's law of heat conduction can be written as minus K. And remember, this is the fluid we're talking about. This control volume has been taken inside the boundary layer for the fluid, which is the fluid thermal conductivity. Since we're talking about the y direction Q double prime, so that is del T by del y, and then we have a delta x. Okay. Similarly, for term number 6, as we did earlier, so we'll write this as q double prime delta x plus del by del y of q double prime delta x times delta y. All right. I'll expand this q double prime as minus kf del t by del y in the whole expression later, because I'll cancel out a few terms, as you'll see later. Okay. So this takes care of terms number 5 and 6. And the next one is term number 7, which we had because of the viscous dissipation. So we said that the fluid, because of its viscosity, generates heat. So it does some work, and that work is called viscous dissipation or viscous work. So the viscous work in was called 7. And the viscous work out was called 8. Okay. So this viscous work in is, as you know, that this is the work done because of the fluid, because of its viscosity. So this is written in terms of the shear stress. So this we write as at the bottom surface we have tau yx as the shear stress, and remember that this is the work done. So shear stress on the bottom plane, when we say tau yx, it's the force in the x direction. If I multiply that by the area, I'm not going into the continuum mechanics here. I'm simply taking just one term because of this shear stress, one force term. So that is tau yx times my area, which is delta x times 1. Okay, so that gives me the force in the x direction. And then since we're talking about the work here, so we have to take a displacement. In this case, since it's the we're talking about the watts, so then we multiply that by the velocity. So this viscous work is proportional to the velocity times times tau yx, which contains the viscosity. So, and then you have delta x, which is the area. So more the area, the more work done. And there's a negative sign here because this work is done by the fluid. Okay. So this is my viscous work in, and then similarly the same idea is being used to write the expression for the viscous work out, which is number 8 on the top. All right, so we have all these 8 terms now. So we will now write them all and write the balance equation. So I've written a dot on the top, so that means the rate of change. And this is, we're talking about steady state. That means temperature is not changing as a function of time here. All right. So let's write the expressions for the different terms we had. So for energy in, so the first term was rho times u, I plus u square by 2, and then we had a delta x. This was number 1. Then if I just go back, then we have number 2 on the right hand side, which is energy leaving the system. So we will write that here. So this number 2 was simply rho u I plus u square by 2 plus times delta x plus, and then we had a del by del x of this whole thing delta x delta y. So this was this whole thing was 2. Okay. Then number 3 was rho v. That was the enthalpy and kinetic energy from the bottom surface, and this was written as rho v, and then you had I plus u square by 2 times delta y. And similarly, we had another expression where we had the same thing. Sorry, this was u square. So this was 3 and this was 4. So 4 is what's leaving from the top because of this enthalpy. Okay, then we had the heat conducting into the system. That was q double prime times delta x, and then this was 5. On the right hand side we had q double prime delta x plus del by del y. Okay, so this was 6, and then 7th was the viscous work in, that was minus u tau yx times delta x. Okay, let's check that. Right, so that was minus u tau yx delta x. Number 7. And then on the right hand side, well, the energy, rate of energy leaving out from the top because of viscous work, that was minus u tau yx delta x plus del by del y of this thing, and then delta y. So we clearly see that we can, there's an equal to here as well. This is equal to. Okay, so this is the left hand side, and this is the right hand side. So let's see if we can cancel any terms here. So this term gets cancelled with this one. Then we have for number 3 and 4. So 3 gets cancelled with this thing. Then in 5 and 6, this term gets cancelled with this term, and then in the 7 and 8 we have this term cancelled with this term. Okay, so what we are effectively left with is well, the left hand side becomes 0, so we'll move that to the right hand side. So what we are left with is so this is the result of second term, and then the fourth one, term number 4, gives us this thing, and then the term number 6 gives us this thing, and then the term number 8 gives us this. So you can see that delta x delta y is we can divide the whole thing by delta x delta y. So we are left with this equation. So our job now is to simplify this by substituting um, the expressions for the various terms here. So we can substitute for q double prime, and we can also substitute for tau yx and simplify the expression. Okay, and we'll also open the derivatives using the product rule. So the first term, which is this one, so let's expand this. Okay, so this becomes rho u that can be taken out, and then we have del by del x of then we have the second term, which is I plus u square by 2 can be taken out, and then we have del by del x of rho u. Okay, similarly, we can do the same thing for the second term. Then I will also expand my q double prime, so I get del by del y, and q double prime is minus k fluid del t by del y, and then my tau yx can be written as mu del u by del y, and this whole is 0. Okay, so now what we can do is we can see these terms. So I plus u square by 2 can be taken common, and then we have simply the continuity equation. What we see is if I add these two terms, let me call this a and b. So I can write that a plus b is 0. From the continuity equation. So that helps us get rid of a and b when added together. Okay, so then I can expand on the other terms. So I get rho times u Okay, so this is from this first term that expands to these two terms, and then this third term expands to these two terms. And if I assume that my thermal conductivity is homogeneous, so I can take this out. Okay, so okay, you may not assume that, so this kf then stays inside the derivative. And then for this last term, the viscous work, then we can again expand this by assuming that viscosity is homogeneous. That's the first one. And this is the second term by applying the product rule on the viscous term, and this is 0. In fact, we can simplify this a bit further. Okay, so let's write that. Okay. Let us look at these terms. These three. So let us write them together. So I can take a rho out, and I can take well, a u out as well. Okay, so I've simply rearranged the terms, and let us see this square bracketed term, this one. This is nothing but our x momentum equation. Okay, so we're talking about a boundary layer here, remember that. So in a boundary layer, for a steady state boundary layer equation, the x momentum equation actually is this one. Okay, so if I quickly recall that, so for a steady state, my well, x, well, let's write a general form of the momentum equation in the vector form. So it will be x and y both. So this is the general form of momentum equation. So in this case, it is steady state. So this term is 0. And we're talking about a flat plate here. If you remember that in our flat plate, the pressure outside the boundary layer, that is the free stream pressure, well, dp infinity by dx is 0 for this flat plate situation. And we can also show by writing the y momentum equation that the pressure outside the boundary layer is can be assumed as the same as the pressure inside. In fact, the dp by dx inside the boundary layer can be assumed to be equal to dp p infinity by dx. But in this case, since that is 0, so that means that this term for the x momentum equation is also 0. So we're left with u dot grad u, and if we taking the x momentum equation, then we simply have this term like this. So this is nothing but u del u by del x plus v del u by del y, and then on the right hand side, this term becomes 0 for the flat plate, and then nu is nothing but mu by rho here, and then we have del 2 u by del x2 plus del 2 u by del y2. Now again, in the boundary layer, we know that the y gradients of the x velocity, which is u, is much higher than the x gradient. So del 2 u by del y2 is much greater than del 2 u by del x2, so we can neglect the latter. Okay, so what we see is that this whole thing is nothing but 0 from the x momentum equation. So we can see that the energy balance actually has been simplified a lot. So ultimately we are left with is simply sorry, I think I missed one term, which is this one. Okay, so we have these four terms, and remember that the rate of change of the enthalpy, a specific enthalpy, is nothing but Cp times change in temperature. Okay, well, it's not a rate of change of enthalpy; it's a change in enthalpy. So we can now write this as rho u, and then we have Cp can be taken out, del T by del X. All right, so we have these four terms remaining in the equation. So let's rearrange them. In fact, I will do it here only. So I write this like this. In fact, I can take my rho and Cp common from the left hand side. So I simply am left with a u and a v, and then I have rho times Cp common. So if you if you write this again, this we have mu by rho Cp, and if you remember why your k by rho Cp, sorry, this should be a plus because we had moved terms from left to right. K by rho Cp was nothing but your thermal diffusivity. In this case, it is for the fluid. Okay. So this is our equation for convection. All right. So this equation, let's understand the terms here. So this one is in fact we call well, the word again is convective term, but the idea of convective comes from the temperature field that is flowing because of the flow. So this just carries the temperature, basically the hot or cold fluid, along with the flow. And then this term is called the conduction or the diffusion term. And this one is called the viscous dissipation. Okay. So this basically, the convective term in this equation is telling us the net transport of energy out of our control volume. Okay, so this convects out the energy out of the control volume, and this on the right hand side, well, the second term on the right hand side, the conduction term, is the net heat conducted into the control volume. So that's the heat that gets conducted into the control volume, and the viscous dissipation term is the net work or net viscous work done by the fluid. So we can roughly understand this as the right hand side contains the net heat conducted into the control volume and the net viscous work done by the fluid inside the control volume generating energy. And on the left hand side, we have the net transport of this energy out of the control volume. So the left hand side balances the two terms on the right hand side. You may also have, in some cases, some heat generation on the right hand side. So that will be some Q dot term that will be included if you have some sort of resistive heating inside the fluid as well, depending on the situation. Okay. So let's look at the ratio of the two terms on the right hand side. So we'll take a ratio of the viscous dissipation term to the conduction term here. So I'll call the ratio of the viscous dissipation term to the conduction term. Now, what we really want to see is in what situations we can neglect one of these terms, or if it's important to keep them. So we'll take an order of magnitude, we'll do an order of magnitude analysis and estimate the magnitude of each term. So let's estimate the magnitude of the viscous dissipation term first. So del u by del y. So when we're estimating this, we can estimate this del u by del y as so the maximum difference in the velocity across the boundary layer is u infinity minus 0 in the y direction. So you have u infinity, and again the thickness of the boundary layer is delta. So we'll call it delta. So this is how we can estimate the magnitude of the viscous dissipation term. And then again the conduction term, which was alpha times del 2t by del y2. So this can be estimated as so del 2t by del y2 again can be estimated. So the temperature across the boundary layer is Ts minus T infinity, and again del y2 can be estimated as a delta square. So when I take a ratio of these, let's give them numbers. So let's call this 1 and 2. Okay, so this becomes, so mu by rho can be written as the kinematic viscosity nu. Then we have an alpha. So this delta squared cancels out. Okay, so this term, in fact, the two terms. So this first one has a name. It's called the Prandtl number. Okay, so it's non-dimensional. And then the second one is called the Eckert number. Okay. And the product of these two is what decides whether we should retain the um, the viscous dissipation term or not. So in this case, well, the product of Prandtl and Eckert number decides whether we should retain the viscous dissipation term or not. In fact, what we see is that for subsonic flows, this product Prandtl times Eckert, which is nothing but the ratio of the viscous dissipation term to the conduction term, is small. So if that is small, then that means is that the viscous dissipation term can be neglected when we are adding that to the conduction term. So So let's well see an example. So let's give some real numbers and then see what this product is. Let's take air at 20 degrees centigrade, which is moving at well, the free stream velocity is around 5 meters per second, and the surface temperature um, of the plate in this case is 60 degrees centigrade. That means the air is cooler than the surface. So it's cooling the plate down. And then we have atmospheric pressure. The Cp value here is 1005 joules per kg Kelvin, and the Prandtl number is 0.7. Okay, so this is the Prandtl number 0.7 for air at 20 degrees centigrade. So that is the ratio of the kinematic viscosity to the thermal diffusivity of air. Okay, so for this situation, let us estimate the product of the Prandtl number to the Eckert number. So Prandtl number is 0.7, and then the Eckert number is U infinity squared, so which is 25. And then in the denominator we had Cp, which was 1005 joules per kg Kelvin. And then we had the temperature difference, which was 60 minus 20, which is 40. And then we can use the difference, so we can use Kelvin here. So if we evaluate this, then this comes out to be 0.000435. Yes, you can see that it is extremely small. It's much less than 1, which is the basis for neglecting the viscous dissipation term for this kind of a situation. So this is quite a realistic situation where you have air blowing at 5 meters per second, and the product is much smaller than 1. So that reinforces our idea that for subsonic flows, Prandtl times Eckert is small, and we can neglect the viscous dissipation term. Okay, so it's always good if we are in a doubt to check this product to see if we can actually neglect the viscous dissipation term or not. Okay, so most of the situations that we will deal with in this course, we can safely neglect the viscous dissipation term in the energy balance equation or the convection equation. Okay, but for high speed flows, supersonic flows, we in most cases cannot neglect the viscous dissipation term. So let me write the energy balance equation again. Now this time without the viscous dissipation term. Okay, so this is the energy equation. I'll say viscous dissipation neglected. We still have the other assumptions that we applied earlier: homogeneous case, steady state, two-dimensional, and so on, incompressible as well. So here, if I go back and write my momentum equation, actually the x momentum equation, well, actually I did that some time ago, so I'll just write that. It's a steady state equation. And on the right hand side, we had nu times del 2 u by del y2. Confirming that here, so you can see that you had u dot grad u, which was nothing but u del u by del x plus v del u by del y, and then you had that was equal to nu times del 2 u by del y2. Okay, so this is our momentum equation. Now remember that in the momentum equation, the unknown is u. In the energy equation, the unknown is temperature. So temperature and u in the two equations are unknown. So if I see and compare the equations, they look extremely similar, except this these coefficients that we have on the right hand side. So what we actually see is that the ratio of these coefficients somehow tells us an information on how the momentum as well as the temperature boundary layers, they differ from each other, because other than these coefficients, the equations look extremely similar, and the equations look extremely similar. So this ratio of these coefficients, nu by alpha, which we just defined as the Prandtl number, it is extremely important. When comparing momentum and thermal boundary layers. Okay. So we will stop here, and in the next lecture we will analyze the energy balance equation, that is our convection equation. From now we'll call it the energy equation, and we will see, firstly we will non-dimensionalize it to get some insight into the behavior of this equation, and this will then be followed by the solution of this equation for this flat plate situation. So we'll be using some strategies, some mathematical strategies to solve this equation, and then once we have the solution, we'll analyze that further to get some more insight into the behavior of the temperature profile inside the laminar boundary layer. So remember that the aim here is twofold. First, to non-dimensionalize it and get some understanding or some insight into the behavior of this equation with respect to the non-dimensional parameters. And the second one is to actually solve it and then understand and analyze the solution. So we'll stop here and then we'll continue from here in the next lecture. Thank you.